Good morning. This video is going to be a little bit different. It's going to be a kind of like a lesson hybrid example. I'm going to be doing it on a whiteboard. It's not going to be a lecture because it's still on diagonalization. And again, we're going to continue on with the diagonalization lecture. So the past couple examples, we've been focusing on diagonalization. The last video, we did a matrix powers example, where if you raise a matrix to some power, we can simplify it and letting it equal to some invertible matrix, and then multiply it by the diagonal matrix raised to that power, which will make it much more easier than just multiplying that given matrix x amount of times. So let's have a little fun with this one because this one's quite interesting, and it involves the exponential, or e, as some people like to call it. And so this is a very interesting guy. Interesting. I can't spell. Because if you remember in calculus, you know that e to the x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus all the way to infinity, which in general will be x to the n over n factorial. And some people use it for estimation. So if you want to estimate e squared, you can just substitute x for 2, and you have 1 plus 2 plus 4 over 2 plus 8 over 6, and so on and so forth to however many terms you want. But let's be a little bit spicy, because mathematicians are just they like toying with things. They like just playing around with things. So what if instead of x, we replace it with a, such that a is a matrix? So, I mean, for starters, you can be like, yo, a, like e to the, so we're gonna take the exponent and raise it to some matrix. Like, how is that? Like, what? That's weird. And yeah, I agree. It is weird. It's very interesting, but it just bear with me. Bear with me for a bit, because this is very interesting. So when we substitute it with a matrix, e to the a will simply be, instead of 1, the matrix equivalent of 1, which would be I, and this would be plus a squared over 2 factorial plus a cubed over 3 factorial, and so on and so forth. And when you look at it, it's like, okay, this is doable. I mean, it's matrix addition and then matrix multiplication, if you want to do that with just multiplying the same thing. But if you recall from the last video, we can rewrite a to the k and let it equal to s, some invertible matrix, times d to the k times s inverse. And when we substitute that in, we will get I plus a, or we're going to substitute a, so this is s d s inverse plus, it's going to be 1 over 2 factorial s d squared s inverse plus 1 over 3 factorial, multiply all that by s d cubed s inverse, and so on and so forth. If we use this definition, a to the k is equal to s dk of x, then that means that a is diagonalizable, which also means it is an n by n matrix. So we are left with, what we're going to do now is we're going to alter this equation just a little bit, just a tad bit. It'll be s d to the negative 1, or not d to the negative 1, s times d times s to the negative 1 plus s times d squared over 2 factorial times s inverse plus s times d cubed over 3 factorial times s inverse. Now, you also, if you remember, another thing that you could recall is if we have a diagonal matrix, just a main diagonal matrix, when you raise it to some power, this will be equal to a to the k, b to the k, c to the k, so on and so forth, down the main diagonal. And because we are working with a diagonalizable matrix, this here is going to be the a's, the b's, and the c. They will all be an eigenvalue. And here's what we're going to do. I'm going to rewrite this equation. So I'm gonna substitute our identity matrix to be equal to s times s inverse, and then we are going to group the d's. So this would be d squared over 2 factorial times s inverse plus dot dot dot. And so what we can do is we can factor out the s. And so this would be s times our identity matrix plus d plus d squared, that looks like a p, d squared over 2 factorial plus d cubed plus over 3 factorial dot 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 times s inverse. And interesting enough, this part here looks very similar to this part right here. And so what we end up getting is that e raised to some matrix A is equal to some invertible matrix S times e raised to diagonal matrix D times S inverse. And that's cool. And so what is e to the d? Well, e to the d, remember, diagonal matrix, when you raise it to some power, is equal to this. So e to the d, if we know that d is a diagonal matrix, e to the d will simply be equal to our identity matrix plus our diagonal matrix, so it'll be lambda 1, lambda 2, so on and so forth, plus lambda 1 squared, lambda 2 squared, so on and so forth, plus, oh, this is like 1 over 2 factorial, and then this is lambda 1 cubed, lambda 2 cubed, so on and so forth, over 3 factorial, so on and so forth. And now what we can do is we can put this all together in one matrix. And so what we end up getting, the identity matrix is just 1, 0, 1 across the diagonal. So when you add them all together, you have 1 plus lambda 1 plus lambda 1 squared over 2 factorial plus lambda 1 cubed over 3 factorial, so on and so forth. And then on the it's going to be the same thing on the diagonal, so it'll be 1 plus lambda 2 plus lambda 2 squared times 1/2 plus lambda 2 cubed over 3 factorial, so on and so forth. It's the same thing all across the main diagonal. And what do you have here? This part here, this is the same exact thing as the definition, or yeah, the definition of what our exponent e is. And it's just e raised to that eigenvalue. So e to the d, where d is a diagonal matrix, it's just e raised to every value in the diagonal. So this would be e1, then this would be e2, and then be e3, e4, all the way down the main diagonal. And that is very interesting. So what we can do is pretty much do what this is called like matrix exponentials. And if we do, we're gonna do a couple examples here with, this is gonna, I guess it'll be the sixth example for this video. We're gonna calculate e to the 1, 0, 0, 1. This is a diagonal matrix, so this is simply gonna be equal to e 0, 0, e. And then same thing goes for part B. If we calculate e raised to the 2, 0, 0, negative 2, then we'll simply get e squared 0, 0, e to the negative 2, or e squared 0, 0, 1 over e squared. And this becomes very useful when we get to higher level math, which would be something that I will discuss in the foreseeable future. But matrix exponentials, they exist. You can get e and raise it to some matrix, which is pretty crazy. It's not something that a lot of people will notice that you can do. But I mean, as like mathematicians, they kind of just they like playing around with things. Not to mention the other case that you've seen in probably Calc 2 is when you raise it to I. So again, that's not a real number, and that gives you a cool little identity, which is pretty much Euler's identity. And so who would have thought that we could do this with matrix? So our last example will be when we have e raised to the 1, 1, 0, 0. So we need to diagonalize this. And so that's just, we just pretty much use the, just like as usual, 1 minus lambda. That will be 1, 0, negative lambda. And so we can see that our eigenvalues is 1 and 0. And so when lambda is equal to 0, we will get 1, 0. Then 1, 0. So our vector will just be 0, 1. And then when lambda is equal to 1, we will get 0, 1, 0, negative 1. And so our eigenvector will be 1, 1. So our invertible matrix will be 0, 1, 1, 1. Our inverse, because it's 2 by 2, this will be relatively simple. So it'll be negative 1, 0, 1, 1. And then to find this will just be equal to 0, 1, 1, 1 times our diagonal matrix, which is going to be 0, 0, 0, 1 times negative 1, 1, 1, 0. And so this will be, oops, I messed up. This would be e raised to the 0, 0, 0, 1. So our e is going to be, or this part is going to be equal to e to the 0, which is 1. Then this will mean 0, and this will be e. So when you do the multiplication, you will get 0, 1, 1, 1. And then this will be 0, 0. Oh no, this will be negative 1. Negative 1. And then this will be 1, 0, 1. And then over here we'll have 0, 0, then 1, e, e. And then lastly will be, that will be 0. And so we will get as our final answer will be 0, this will just be e, then this will be 0, 0, then this would be -1 plus e, so e minus 1, then 1, 1, then 0. So this will be our answer to e to the 1, 1, 0, 0. And that's pretty much it for this video. It's pretty much it for this lecture of diagonalization. There's so many things you can do. There's so many questions they can ask you. Overall, it all boils down to finding the characteristic equation, finding your eigenvalue, eigenvectors, finding your creating your invertible matrix, and keeping in mind that the eigenvalues and eigenvectors line up within the columns. And then just do whatever you have to do. If you have to raise it to some power, have to find a diagonal matrix or whatever to ask, or raise it to the e, or you can do all those things. And so yeah, that is it for this lecture, and I'll see you guys in the next video.